At 1:23:40 a.m. on April 26, 1986, operators at the Chernobyl Nuclear Power Plant pressed the EPS-5 button. It was a standard command for an emergency shutdown, meant to stabilize the reactor during a routine safety test. While designed to drop control rods and halt the reaction, the mechanism had the opposite effect. Within seconds, the power output surged to an estimated 300 gigawatts, far exceeding the reactor's physical limits. The disaster was a collision of two forces: the unstable physics of the Soviet reactor design and a state infrastructure that was about to be tested by a catastrophic failure. The Soviet RBMK-1000 was a massive graphite-moderated powerhouse. It was a cornerstone of the energy grid, designed to provide high output at a low cost, but it lacked the thick containment structures common in Western designs. This cross-section shows the core's cooling system. In this design, the reactor had a positive void coefficient. When the cooling water begins to boil, it creates steam voids. Unlike most reactors, these voids actually increase the rate of the nuclear reaction. This creates a feedback loop. More steam leads to more reactivity, which generates more heat, boiling the remaining water even faster. To stop this, operators used boron control rods. However, these rods were tipped with graphite. As they enter the core, that graphite displaces water and momentarily spikes the reactivity at the bottom of the channel before the boron can take effect. Internal records show that while the designers were aware of these characteristics, they did not effectively communicate the danger to the plant personnel. The standard operating procedures left the crew unaware that their failsafe could act as a detonator. The machine was physically unstable at low power, requiring only a specific sequence of procedural errors to reach a point of no return. This log from April 25th shows the beginning of the crisis. A planned safety test was delayed at 1400 by the Kyiv grid controller. The reactor was forced to stay at half power for 9 hours, leading to a buildup of neutron-absorbing gases in the core. By the time the test finally began after midnight, the reactor's power had plummeted to just 30 megawatts. The core was poisoned, making it sluggish and difficult to control. To regain power and keep the test on schedule, operators pulled out nearly all of the reactor's control rods. They were operating the machine with almost no remaining safety margins, effectively disabling the reactor's primary brakes. When the test started, the cooling pumps slowed down and water flow dropped. Inside the core, steam voids began to form rapidly, and the thermal power started to climb at an uncontrollable rate. Desperate to stabilize the unit, the operators had unknowingly aligned every one of the reactor's design flaws, ensuring that any attempt to shut it down would trigger a meltdown. This digital printout records the final attempt to regain control. At 012340, the EPS-5 button was pressed, sending the graphite-tipped rods into the surging core. The resulting explosion blew the 1,000-ton upper shield clean off the reactor. As seen in this aerial photograph, the core was exposed to the atmosphere, releasing massive amounts of radioactive material directly into the sky. Local firefighters were immediately dispatched to the site. They worked amidst the highly radioactive rubble without specialized protection, having been told by plant management that they were fighting a simple roof fire. As the physical destruction of Unit 4 peaked, the disaster began to shift from a local industrial accident into a massive statewide emergency. In the days following the blast, the Soviet state worked to control information. This declassified KGB document is marked strictly secret. The authorities downplayed the scale of the disaster, prioritizing the appearance of stability over public health. This view of Pripyat shows the cost of that secrecy. The city's 50,000 residents were not evacuated for 36 hours. While the state maintained a facade of normalcy, the population was being exposed to high levels of iodine-131. Official acknowledgement only came after radioactive clouds triggered alarms at a nuclear plant in Sweden. Facing international pressure, the Kremlin finally admitted that a serious accident had occurred. Cleanup efforts were desperate. When specialized remote-controlled vehicles like this one failed due to the intense radiation, the military deployed biorobots, soldiers who shoveled radioactive graphite off the roof in 90-second shifts to minimize their exposure. The state's focus on containment of the news rather than the radiation significantly increased the health impact on the first responders and the surrounding population. Environmental damage was severe. This area, known as the Red Forest, saw its pine trees turn brown and die within weeks. Decades later, radiation warning signs remain a permanent feature of the landscape. Later investigations shifted the blame. This report notes that the scale of the accident was not determined by the operator's actions, but by a fundamental lack of understanding from the scientific managers who designed the reactor. In the years that followed, the Soviet Union was forced to retrofit all remaining RBMK reactors. These engineering changes were a tacit admission that the original design was dangerously flawed. Today, the exclusion zone is a rewilded territory where nature has moved back into the abandoned ruins. It remains a 2,600 square kilometer area that cannot be safely inhabited, serving as a reminder of the consequences when engineering is compromised by political pressure.